So, dear colleagues, dear friends, welcome everyone to the 16th IFS Seminar. Today our speaker is Armen Vagharshakyan from the Institute of Mathematics. Armen has spent some years of professional work in the United States, and his main field of research is complex analysis and ramifications thereof in other branches of analysis. Today, hopefully we'll learn a few things about all that from Armen, and the title is Uniqueness Theorems in Analysis. So I'll let Armen decide whether he wants to receive questions during the talk or he is planning to make breaks to receive questions, or I'll let him decide on that. So yeah, please, Armen, now you have your time.
Okay, thank you for your invitation. As I said, I picked this topic because it somehow goes very well with a general audience. I apologize to people who might have heard this topic in this or that way before. However, I tried to put a different logical emphasis during this talk and try to emphasize use of complex analysis in general. Why would you need complex analysis if you are just a normal human being? So let's start. So here's a result that I wanted to point out to you, a very like a high school type of result. So suppose P is a polynomial. We start thinking about functions as just polynomials at first. Let's see what happens. And here's something I put, a condition that points Z1 up to Zn are its zeros. So the question is, what can be inferred from this condition about the function's growth at infinity? So please pay attention. I didn't say that these are the only zeros of that function, nor I said that these zeros are distinct from each other or counted with their multiplicity. Just some general information about the function. Z1 to Zn are its zeros. And it turns out that the following dichotomy result holds. Either that fact that some endpoints are its zeros is enough to claim that the polynomial P is identically zero, or it turns out that it has to grow really fast at infinity. So you can see the speed of the polynomial at infinity. So it cannot have this middle ground. And this is, in a way, a reason called for this type of theorems to be called uniqueness theorems, because if we additionally impose a condition that this growth at infinity should be bounded, then by only knowing that it's zero at these points, it turns out that it has to be identically zero everywhere. So uniquely determined by the values at these points. Now, this is type of middle school type of problem, but I wanted to run through it just so that we flow with the things that come up. So here's, I point out an algebra type of proof. So first thing one would do is to recall Bézout's theorem that says that if you have a polynomial, then the fact that Z1 is a zero for that polynomial is enough to carve out a factor of Z minus Z1 out of it. Now you use that Z2 is zero, Zn is zero, and so on, and you carve out many factors one by one out of P. P being equal to this product times some remaining non-zero polynomial. Now what you can do is to turn this product into a sum by doing some kind of combinatorics. You end up with a polynomial whose highest power is Z to Zn times something other, which is not identically zero, say. It grows with some speed, so P grows at infinity with the speed of Z to Zn at least, and here you get it. So with this initial assumption that P is not identically zero, from the fact that Z1 up to Zn are zeros, from some combinatorics, we have it. Of course, problem will arise if we think not of a usual polynomial, but of some kind of infinite product. Then we will have problem turning these factors into sums, and all the mess would come up. So these types of things are being done. So for analytic functions, turning it into an infinite product just by knowing the sequence of its zeros, making sure the product converges by tempering the product. This is called Riesz's theorem. Then doing all these combinatorics. So you could see works like that being done just by trying to push whatever we know for polynomials of finite order to analytic functions. So informally, pretty informally, they say that analytic functions are polynomials of infinite order just by trying to mimic the results that hold for polynomials to these infinite sums. However, one can use the complex analysis methods to achieve the very same result in a pretty different way. So a high school student would not know complex analysis, but you could see how this could be beneficial for you. So first, thinks that P is a polynomial, as I said, so a priori you know that it's a certain sum of monomials, A0, Z to Zm, and so on. The power of the sum, I don't know, something. I put M as the power, so P has degree M. I don't know what M is, but if I assume P is not identically 0, some M exists. And then the next thing I would use is something called maximum principle. So this maximum principle would work for analytic functions, of which P is an example, and analytic functions are these solutions of Cauchy-Riemann differential equations. There's one more type of differential equations that are very visible, called a Helmholtz equation relating to minimal surfaces. So I wonder, could you see this picture there? Yes? This one here?
Yeah, we can. It's small, but we can see more or less. Yeah.
You have a guess what it is, right?
Yeah, it's kind of a saddle surface.
Yes, but it's a photo of some very physical object. This is a soap film. When you have these bubbles and you create soap films, you know, when kids play. Мыльные пузыри. So this is a picture of it. So this is a boundary, and this soap, you know, is there. It has a very thick surface, and the differential equation that answers for it is Helmholtz equation, not really Laplace equations that would be proper for the real part of an analytic function, but still you could see from just physical observations that I hear some kind of voice background, but what you can see from physical observations that a maximum of this function will necessarily be achieved on the boundary. So by making this type of soap film, it is impossible to have some kind of bump of soap in between. It will be laid out hanging from the boundary of these things. So the maximum of this function will be achieved on the boundaries. This is a very real physical effect that happens for the Helmholtz equation, type of elliptic equation, and it also holds for Laplace equations, for harmonic functions, and maximum principle also holds for analytic functions. So you would expect that in a very, very large disk, the maximum of this function will be the same as the maximum on the boundary, on the rim, or on the circumference of that disk. And from there, it turns out that the function P and its main part, A0, Z to Zm, have the same number of zeros. So you see, this maximum principle allows you to claim the number of zeros of a polynomial without calculating this zero anyhow, just by looking at its main term. So P is the main term plus something other, the main term z to the m. What are zeros of the function z to the m? It's a 0 calculated with multiplicity m, and the claim of complex analysis is that if you have some kind of more, lower order terms, then in a large disk, what they can do is just distort these zeros from the point 0, where there are m of them, to some other points, but without adding or reducing the number of zeros. So P in a really huge disk has exactly m zeros. And we know a priori that it must have n zeros, so n is smaller or equal than m. So P is a polynomial of degree at least n. Well, from there, the speed of P at infinity follows. You see.
Excuse me, Armen.
Yes.
Sorry for interrupting. Do we have questions in the audience? Because you didn't specify whether they should raise hands or whether they should interrupt you. So maybe
let's just go with the flow. If there's any question at any moment, please go ahead.
Yeah, please interrupt the speaker if you have a question. Just to say, yeah.
Yes, so you see, this way, this maximum principle saves us from actually assuming what the zeros of the function are, and from all this combinatorics, which is possible to do as a student, but it gets much harder for infinite products or for much like more general functions than polynomials are. But this maximum principle really saves us. We don't need to know the zeros. We just have this principle, which could be observed just physically, and from there, our claim implies the dichotomy claim. Now, I wanted to go forward and to say something more. This is just a conceptual thing. Then if you think of a polynomial, how in the world do you think what a polynomial is? So, like in a school, you would think of it as a graph, as a dependence, as a law between x's. So you take a value of x, plug it into the formula, and get P of at x. So it's some kind of graph of x's and P of x. But you can also think of this object algebraically by saying that polynomial is a sum of three functions. Each of them is a monomial. This is the function identically 1. This is the function x. This is function x squared. So you take some kind of simple functions, and from these simple functions, you create by multiplying them by numbers or by summing up a new object. So this kind of algebraic view on polynomials. The thing is, both views have their benefits and have their downsides. For example, if you want to understand what the zeros are, you just look at the graph. But what if you want to understand, for example, the derivative of a polynomial? It takes, undergraduate calculus and all this epsilon delta language to interpret a derivative of a simple function, as a polynomial is, in terms of this tangent lines and limit and so on, and all this epsilon delta language. But if you just think at the end, you can just define a derivative of a polynomial just by a new polynomial whose coefficients are derived from the coefficients of the original polynomial by just some kind of shift and multiplication. So if you think of a polynomial as just this range, just vector of three coefficients corresponding to the things in front of functions 1, x squared, then derivative is very easy. So in terms of this vector of coefficients, derivative is easy. But in terms of graph, derivative takes epsilon delta. And the other way around, in terms of zero, this is easy. But in terms of understanding the zero of a function whose coefficients are given, you need some formulas, or maybe you can't even express it in simple terms. So some things are easier in this language, some things are easier in that language. That's for polynomial. Further on, if you go on and start thinking about, say, trigonometric series, there's a whole branch of mathematics trying to relate the properties of them as functions, like things that you can see on graphs, and the properties of these corresponding frequencies, may I say. So relating them one to the other, and a major part of harmonic analysis is just about that. Two more points on this very simple example before we dive in things more elaborate. In here, you think of it as a function, then you think of it as a vector of coefficients, or say frequencies, or things like that. They're like separate things. This is a function, and this is a vector of three components, a function and a vector. They kind of live in different places, the time place and the frequency place. And the thing is, we may want to relate them to each other so that they are not that separated out, and kind of merge in one into the other. And another thing is the following. If you think about a polynomial, suppose you are given a value of x, and then you can evaluate p of x. That's what happens in physical observations, right? You have a signal, you turn in points, you get values. Now, A2 will correspond to the largest component of its speed at infinity. So if you think of px at infinity, of course, it grows as fast as x squared, and the coefficient in front, A2, answers for that. So that way, if you kind of have a priori information about p speed at infinity, you can restore A2, and then take out A2x squared, restore A1, and so on. So this is something that you can do. You can relate to these coefficients by understanding p's growth at infinity. But what if you have a trigonometric problem? Here we have it. So see, I'm not using a complex numbers at all in this first line. It's just a polynomial trigonometric one, sine x and sine 2x. I'm sorry here, sine x and sine 2x. Two functions, two coefficients, and I specifically emphasized for you, x is in R. So, you know, a polynomial on its own, just some frequency and some other frequency. So what happens is that, what if you want to restore B2 just by looking at its values at some points? It will not be as easy as kind of trying to understand its asymptotics at infinity, because it doesn't show up at infinity. It's a periodic one. So there are two periods. You have to look at the periods rather than the asymptotics at infinity to guess what B1 and B2 are. And again, this question arises that from one point of view, you think about it as a function, x relating to t of x, and from another point of view, you think about it as its a spectral decomposition. The spectrum will have 2 points, B1 and B2. So they are like separate animals living in separate places. What if we join them with each other? So what if instead of sine of x, we think of sine of z, of a complex variable? First line, like in Wikipedia, sine of z is e to the iz plus e to the negative iz divided by 2i. So I bluntly plugged in, and now instead of thinking of this function only taking values at real numbers, I think of them, this function, as taking values at complex arguments too. So this seems like messing up things even more, as if we could understand much about t of x at real axis. Now we have to look at it on the whole plane. We have to introduce complex numbers, their products, and all the mess. But follow me on this one. What if we think of z not as x, so the real axis, but as of iy, so the imaginary axis? So instead of thinking of t of x as x taking value at r, we think of t of iy, y taking value at r, and let's see what happens. So instead of z, I just wrote iy, and I just use the things that I squared is -1. Here's what I got. I got a different function. Now, instead of sines, it has exponents. So sines kind of merged into exponents, just it's the same function looked upon on the real axis or the imaginary axis. On the real axis, it's sines. On the imaginary axis, it's exponents. And look what happens as this y goes to plus infinity. The speed of it as y goes to plus infinity. So equating -1, this goes to 0, this goes to 0. This is exponential, but this is of higher speed. So e to the 2y. And so the highest speed of tiy as y goes to plus infinity corresponds to the coefficient b2. So if you just look at the speed of this function t, but not on the real axis, rather on the imaginary axis, if you look at its asymptotics, then in this way you can restore actually the coefficient b2, something that you could do with a2 with polynomials, and you could not do here because that would be periodic. So this is maybe one type of argument to look at the functions which are usual for us to look in real plane, to look for them in the complex plane, because here are interesting things happen. Let's go ahead and see what can we carve out with this type of thinking when we think of functions as things in complex variable 2. We already mentioned the maximum principle. We mentioned how we can gain coefficients from asymptotics. Now, let's go ahead with this very thinking. We can say that if we have a polynomial and if 0 and n-1 are its zeros, so remember, first we thought of some zeros at z1, zn, we didn't specify them in any way. Now we think of them as integers, 0, 1, 2, 3, n-1 is 0. Then knowing these points where p is 0, we can actually say things about p's coefficients. This is, for example, Vieta's formulas, like, for example, you are all familiar with Vieta's formulas for like square polynomials that relates zeros to coefficients. And if we have more, we can also have these relations. So this spectral things, these coefficients, can be somehow inferred from information about these zeros. There is this relation for polynomials. And there is also something like that for trigonometric polynomials. So think of a function sine pi z, just that function. We know it's 0 at integers. And now I make a step which takes some kind of explanation for math students, but needs less explanation for physics people, is that you restore g by writing its integral over whole complex plane of the exponent with a measure, when the measure is the sum of two Dirac measures. So recall, Dirac measure at a point is something that assigns one of a function and is 0 otherwise. I was wondering if Dirac measure is okay with you guys?
Well, I guess Dirac measure was introduced by us, guys.
Yes, that's why I'm saying I don't need to talk anything about them for physics people. So you have Dirac measure here and there. You plug in this measure into there, and you get sum of two exponents. But I just was talking about sine function being a sum of two exponents. So this expression is actually working if you think of this measure as a Dirac measure. So you have a representation of a function sine as an integral over complex plane, not real plane, complex plane, because this measure is supported on two complex points of a certain measure. So you have this integral representation for this function. So you see what happens just in the slide before. I'm taking something normal, sane, and usual and messing up it. So it was sine. We were thinking about it as something very familiar for it. I mess it up. I generalize it, I think it as an object that is an integral of exponents over a measure. So that's a part of functional analysis. When you try to generalize it and look at a G not as a function, but as sometimes measure as a functional acting on these exponents. So it's over making your thoughts overly difficult for something that isn't worth it. But when you go to that level of abstraction, some things become more visible. This is a measure. I wrote it down, Dirac here. Now, here's the thing. For I pi, which is a point, think of the corresponding point e to the I pi. And think of the corresponding point e to the negative I pi. These are both negative ones. So this change from I pi to the e to the I pi and from negative I pi to the e to the that makes this new measure, which was generated from this mu to a new measure nu, to be zero, because they are both the same points, negative one, you take one from the other, okay, you get zero. Now, I made some kind of strange thing. I wrote some kind of integral. I introduced Dirac functions. I had to go to the complex plane. I made some change, which I didn't explain in anyhow, but I ended up with zero. And we know that g of z, being the function psi, is zero at points 0, 1, 2, and so on. And it turns out that these two facts, this line 2 and this last line, are related. So zeros of the function and this fancy property of mu measure corresponding to that function are in fact related. So let's think about a trigonometric polynomial. You see there are terms, there are exponents. We must be used to complex numbers by now. Let's assume it's zero at these points. Let's assume, then I can write the function g, irrespective of this fact, as an integral of exponents with respect to a measure. So I think of g as some kind of measure acting on exponents. And it turns out that for this measure, I perform the same change from I something e to the I something, then this fifth condition is equivalent to the second condition. So if someone tells you a priori, if you have a trigonometric polynomial, what is a necessary and sufficient condition in terms of its coefficients for that polynomial to be zero at that point, this is not actually extremely trivial. There were papers on that in the beginning of the past century trying to prove these facts. So, but here you kind of grasp the idea. It's a generalization of the same fact. So this measure in a fancy way corresponds to the zeros of this function. Just like when you know zeros of a polynomial, then their coefficients are related in a fancy way by Vieta's formulas. So far, so good. Can I go to the next slide?
I guess so, unless we have questions.
Well, if we don't, then just let's go one step more and let's be ready to dive in, not into trigonometric polynomials, but into analytic functions in general. So I think of an analytic function in the right half plane, and I think of that function having zeros for all these points. It was, I go one slide back, a trigonometric polynomial, and it has zeros. Now it's an analytic function in general. It has zeros at these points. And it turns out that a corresponding dichotomy holds. Either an analytic function has to be identically zero, or it has to grow really fast on the imaginary axis. Remember, we dealt with imaginary axis before with trigonometric things, and growth on the imaginary axis has something to do with its coefficients and with a spectral decomposition. So here we go, but not for trigonometric functions, but rather for analytic functions in general in the right half plane.
Excuse me, Armen, when we say it is holomorphic in a closed domain, do we need in an open neighborhood of that domain or what?
Yes, a little bit more. So here's the thing, for this original formulation, Carlson needed for it to be holomorphic in an open domain that contains the right half plane. So imagine this part plus a little bit kind of more to the left, but there are generalizations, there are neater things that would only need like a right half plane and so on. I try to kind of impose more conditions and show weaker results, but emphasize on what is going out, emphasize on relations. So at this moment, you pretty much feel that this is something that is quite natural. This fact about zeros behavior on the imaginary axis, which is a whole different axis. You know, this is on the real axis, 1, 2, 3. This is on the imaginary axis. Look, y belongs to r, y belongs to infinity, but it's iy. So g at the imaginary axis. So behavior of this analytic function on one axis imposes behavior on the other axis. This might sound strange a priori, but we checked for trigonometric polynomials, then yes, you know, things like that hold, because this might look like this asymptotics of that. So again, I want to say that there's a reason to call it uniqueness theorem. It's just if we impose a condition that g doesn't grow that fast on the imaginary axis, then a function which is 0 at natural numbers is uniquely determined, and it's only the identically zero function. So in general, you can determine an analytic function on its values at these points. If you know a priori, then its speed on the imaginary axis is not that huge. So this is a uniqueness theorem, just like a uniqueness theorem that we had for polynomials. It's just the polynomials one is a school student problem, and this needs a bit more work. Now, I want to dive into this uniqueness theorem things, because if you kind of list through analysis in general, you happen to several theorems which are formulated just like that, in uniqueness sense. So this one is called Brother Riesz boundary uniqueness theorem, and it goes as follows. So we think of a Hardy space in disk H1. So Hardy space is disk is that this time we think of functions that are analytic, and there's a certain condition on its growth as it goes to the boundary. So we think of function which is analytic in a circle, but not necessarily out of it. So it is growing towards the circle, and possibly sometimes getting, you know, unbounded when you get to the circle. So you can not necessarily get out of the circle, but inside the circle, there's some growth condition. You allow it. And then it turns out that what happens on the boundary is there's also some kind of uniqueness result, that it's either identically zero, or it can vanish only on a very small thing, only on a subset of the unit circle of measure 0. Recall here, either it's identically 0, right? Or when you think of it being 0 at all numbers, and you have to kind of miss one of the numbers, because if it's everywhere or all this n, then it's identically 0. And here is the same. If you think of a boundary functions, as soon as you miss a set of positive measure, you just become identically 0. So I was wondering if the notion is measure is comfortable with you guys.
Yeah, it is with me at least. But
yes. Well, the thing is, this is one of the very first theorems that uses the notion of measure at all. So when we learn about measure, you know, if you talk like a textbook, you know, Riemann integral, then Lebesgue integral, then the sigma algebra, sigma additive, and so on and so on, that's the construction. But one of the first places when it was made use of, one of the first reasons, was not like take a Riemann integral and think of a function, of associating an integral concept to a function more general than the Riemann integral, but for these theorems. Look, 1916, not very far away from when Lebesgue developed his theory. So this is one of the fundamental things that is necessary to think of measures, and one of the places when measure comes into play when you think of you know, physical considerations. And these two theorems are related. If you think about this, you see the speed at infinity, logarithm GIY. Okay, we talked about this imaginary axis. This is tempering logarithm. This is speed. You see this number, pi. Pi is half of a radius of a circumference, which is 2 pi. So if this has to be larger or equal than pi, then it has to fall out of the interval negative pi pi. And negative pi pi is all the argument can run when you have a circle. And these two things are related. There's some kind of circle going around, because this theorem, Carlson's uniqueness theorem, which deals with all this analytic function in half space, closed, open, whatever, is actually directly related to this thing. Because if you think of analytic function in this half spaces, just as, I'm going back one slide, just as a trigonometric polynomial could be interpreted as a measure over exponents, and that way you could restore it, an analytic function could be interpreted as a more general measure over exponents. Of course, this time not the direct measure, but generally speaking, any measure. And this measure, it turns out, has to leave its support, has to be cut away from these 2 points to give a non-trivial example of a function which is 0 here and things like that. So if you want to cut away its support from pi I, negative pi I, if you take this interval, I wonder if you can follow it. See the interval negative pi I? It goes up to pi I. I roll it. I take the circumference. Hopla. So negative pi I to pi I. If I roll and take a circumference, you end up with a circle, and all these things could be fit inside. So you would get something like that, a situation like that. And here we necessarily know that the function on the boundary can vanish only at a set of measure 0. And here's the corresponding measure. Have to fill in all these things and maybe more to give an example of function like that. And if it fills everything, then its growth at infinity has to be larger than pi. So in this interesting way, these two uniqueness theorems are related. But even more than that, you go ahead and think of what are other theorems that might be thought of, might be called uniqueness theorems in analysis. And if you're taking like a undergraduate in mathematics, there are 2 more theorems that one might run into, uniqueness theorems. Here's the one. So this is by George Cantor. Cantor is in his PhD, for his PhD, he was given the following problem. Suppose you have a trigonometric series. So these are not a trigonometric polynomial, but a trigonometric series. N ranges from negative infinity to infinity. And suppose it converges for all theta to 0. So the sum is 0 for all theta. It turns out that these coefficients are also 0. So the only way you can sum up a sequence of exponentials to end up being 0 is you just start with 0 all the way around. You cannot kind of cook up different exponential functions to get to 0. They must have been 0 from the way start. So, you know, for several, if you have several trigonometric things, ei theta, e2i theta, and so on, just like several of them, finitely many. It's a fact that you cannot cook them up, consider a polynomial out of them that you can make to be identically 0. In other words, these as functions are independent, linearly independent. But it turns out that even more than that, if you take the sequence of e, I, and theta, you cannot cook them up in this infinite sequence so that all of them become 0. The only way, the unique way of the sum being 0 is that all these coefficients tend to be 0. Now, Cantor was thinking about generalizing that, saying, you know, what if it doesn't converge for all values of theta to 0, for all the intervals of 0, but like for all the interval except 1 point, except 2 points, except 3 points, you know, would we still be able to claim something like that? If we have this series, if it's 0 everywhere except a point or two, then all the coefficients are 0. He was working on that. And then he's going next. He was thinking about what if we throw up not finitely many things, but more things? What if we throw out an interval? Would it be possible? What if we throw out not an interval, but something that is somehow larger than finitely many points, but smaller than an interval, informally speaking? And what are those animals? And if we throw them out, and if we claim that this series is 0 out of this exceptional set, will we be able to claim something like that? And it is his thought, and it is his work in that area that brought us to the measure, and to particularly to the sets of 0 measure, to the exceptional sets of trigonometric series. So now in Armenia we have a whole school of people working on trigonometric series, working on the ways of their summation, working on the way of understanding exceptional sets in that set. So headed by academician Vagharshakyan, who just developed one of their kind of research areas is developing this kind of point of view and understanding that. But if we kind of don't dive into that, just think about this theorem, it turns out that this theorem, being a uniqueness theorem, is equivalent to this theorem on the other theorem. So from Riesz boundary theorem, you can imply Cantor's theorem. From Cantor theorem, Carlson, from Carlson, Riesz, everything. There's just kind of one uniqueness theorem, and quite a neat one, this one. And more than that, so if you think about this physics, you know, these physics people, you know, sometimes they think about, this thing. Shannon-Nyquist Kotelnikov theorem. So, you know, in Russian Wikipedia, it's called Kotelnikov theorem. In the English Wikipedia, it's called Shannon-Nyquist theorem, without any mention of Kotelnikov at all. So this is the US part, this is the Russian part. And of course, the truth is the first person who proved it was neither of them. It was a British mathematician. So here's the way it is phrased, and I tried to follow this physics type of informal phrasing. So you have a signal, it's an infinite signal. This signal is evaluated at points t, ranging from minus infinity to plus infinity. And you want to restore that signal by sampling its values at points who are separated from each other by step h. So you have a signal, you don't know what it is, you only can evaluate at discrete values, but in this ideal case, there are infinitely many values from minus infinity all the way to plus infinity, separated by step h. So you want to get the value of x at any point just by sampling them at these points. Of course, if you don't know anything about the signal a priori, it might just have just a random bump in between those values, and there's no way you can restore a function with a random bump just by knowing its values at different points, naturally. But if this x is some kind of, in the frequency plane, it's a sine x or sine 2x or sine of something x with their frequencies bounded, then you would expect it not to have a bump, because a bump would correspond to sine of, I don't know, 100x, so would peak in the frequency plane. So if this signal x is kind of smoothed out and doesn't have random peaks, bumps, and its frequency set, its spectrum is somehow bounded, then you would expect it not to change fast enough in between values, and in this way somehow the values separated by some step h would be enough to restore your function. And in fact, here is this restoring thing. This is sine x over x. This is the sampling. So sine x over x is like a typical signal that you have. And if you sum it over all integers with interpolation step necessarily satisfying a bound that depends on highest possible frequencies that x might have, then you would restore the signal. And consequently, if the function x has a bounded spectrum, and if you want to sample it at points which are separated from each other by a value dictated by that spectrum, if it turns out that at all these values the function is zero, then it's necessarily zero. So type of uniqueness theorem, it's zero at this point, separated out from each other, then it's zero anywhere. So this is a consequence of the Shannon-Nyquist Kotelnikov theorem, which from that point of view could be viewed as uniqueness theorem, because it's uniquely determined by values at this point. And it turns out that this Shannon-Nyquist Kotelnikov uniqueness theorem is equivalent to Cantor's uniqueness theorem about summing up functions without some kind of exceptional set, equivalent to the Riesz brothers' boundary uniqueness theorem about analytic functions in a disk, and in turn equivalent to Carlson's boundary uniqueness theorem about the growth of a function that is analytic in half plane. It's 6:50 Yerevan time, and I finished my talk.
Thank you very much for the very intriguing, interesting talk, Armen. So here we have a lot of time for questions. Please, questions from the audience. Maybe as a warm-up, I begin asking a couple of questions, if you don't mind. Yeah, so it feels like, at least from a side, that there is somehow everywhere, at least in some of the relations between these theorems, there is some Fourier transform hidden, which you deliberately are trying to hide from us. Because this, bounded spectrum related to the the size of the uniqueness mesh and this kind of things, these are related to the, well, Paley-Wiener theorems, which are somehow written on the very bottom of your slides.
Oh, yes.
Yeah, so they are giving us some hints. And then also this Hardy space, and then if you translate the Hardy space from the unit disk to the half plane, and then use the Paley-Wiener theorem for the Hardy space, you'll probably get something that's related to the claimant. So the general feeling is that everywhere there is something like, and the Cantor's theorem is also basically saying, it's basically a surjectivity result for the discrete Fourier transform, if you wish. So you have been hiding the Fourier transform from us in a sense. So maybe you can comment on that a little bit. Thanks.
Here.
Yeah, here not quite. It's more of well, complex analysis, entire function theory kind of thing. Where
so here's the thing: if you think of function, you can think of its Fourier transform, integral fx e to the I omega x dx.
Right.
And as I was trying somehow to convince you, sometimes it makes sense to go over that and not to think of real things, but think of imaginary things. So if you think of the Fourier transform just on its own, if you think of a Fourier transform, it associates a real a function of real argument to a function of real argument, right? Fx and f hat x. Don't think in this narrow-minded way that f hat x lives only on the real line. Define f hat x also for the complex values. Now, many things that would sound a bit unnatural for this Fourier transform thing will sound much more natural if you go and discuss the Fourier transform for complex values too. So if you think here, what do I have? Okay, I have an integral of a plane. Forget that. I can make it an integral of a real line. I have a measure. Well, Fourier transform of measures is a topic quite familiar. And here I have e to the omega z, right? You see? Here. But here, for this omega, which I generally thought of a complex number, you can think of it as Iy, then it comes to the Fourier transform, or you can think of it just a real number, then it comes to something complex. So this is a transform which is more general than the Fourier transform. So sometimes things like that would be called, depending on this area of use and depending on how they are written, that would be called Borel transform. Sometimes that would be called Mellin transform. But for the way that I write things, that would be called Laplace transform. So Laplace transform is a generalization of Fourier transform, trying to understand it as thinking of Fourier transform taking values on the complex plane. And it's this type of generalization that allows us to get integral representations for functions which are analytic on half plane, and to develop an analog of theory for them that you would otherwise get by using Fourier transform in the real case. So a more general concept than the usual Fourier transform allows us to work it out.
Yeah, well, when we speak of Paley-Wiener theorem in its most classical formulation, you are using not just the Fourier transform from real line to real line. You are using Fourier Laplace transform, yes, of course. Exactly. You are using Fourier Laplace transform, but it is still an integral along a line in the complex plane, but along a line. Yes. Here you have an integral over the full C, yes, which is qualitatively different, right?
Yes. So somehow, for example, in order to develop some kind of neater results on Carlson's theorem, I had to go to the complex plane. I had to go from a line all the way to there to achieve results and integral representations for proving some generalizations of Carlson's theorem. So yes, this is a more general concept that ultimately derives from the usual Fourier transform and from the usual Pelly-Wiener technique, but it's more general, and it's this generalization that allows us to treat functions which are analytic on the half plane instead of just the previous results that would think of functions that are, say, entire and analytic everywhere. So yes, I had to kind of think of a more general technique than Fourier transform to work out some of the things here. Yes.
Right. In that case, so for the usual Fourier Laplace transform, we have some kind of surjectivity, or we have some kind of description of the image of classical function spaces in the Fourier space. Like the Pelly-Wiener theorems are telling us basically, if you have an square integrable function on the half line, then its Fourier transform can be analytically extended, and it has certain exponential growth towards the imaginary axis. Or if you have a smooth, compactly supported function on the real line, then you have an entire function. So in a sense, it allows to obtain some explicit or more or less explicit description of the Fourier images of certain useful function spaces. Now, with your definition of transform, which is, well, it takes the integral over the entire complex plane, I'm wondering if it allows to describe to some extent the images of some standard function spaces, say.
Of course. So here's what happens. As you mentioned, the Pelly-Wiener theorem, actually, there's the Pelly-Wiener theorem. And in general, a Pelly-Wiener type theorem is any theorem that takes a function space, think of its Fourier transforms or whatever Laplace transforms it is, and tries to describe where you end up with. So there's a whole kind of area of research talking about what if you take a space of functions, think of its Fourier transforms, and what space of functions do you end up with, isometries between these functions, and so on. It's like a whole branch of harmonic analysis called Pelly-Wiener type theorems. And of course, I had to kind of develop things like that. And there are many more things like that. For example, I mentioned the real analysis group in Armenia. I need to mention the complex analysis group in Armenia too, who were thinking about having this Fourier transform living on certain lines in some weighted spaces and so on, and it restoring some classes of functions. This is a branch of work pioneered by academician Vagharshakyan, and you would have many results of this type in the Armenian school of complex analysis. So yes, this generally speaking, a theorem that relates properties of a function or a space of functions to the properties of its Fourier transform. Where does it end up with? It's called a Pelly-Wiener type theorem, and there are many of them. So in a way, what you think of a polynomials, when you want to relate zeros to the coefficients, it's also something like that.
Yeah, that was the motivation for my question in the first place, because everywhere I'm seeing some kind of versions of a Pelly-Wiener theorem, if you wish, in
Yes.
all the theorems, but you don't spell them out in that way. You are trying to
avoid terms.
Yeah.
I try to avoid terms. I try to avoid talking about spaces of exponential growth, Hardy spaces, Bergman spaces, duality of spaces, and all the mathematical apparatus. I try to water it down as much as I can.
So let's look at this third line in blue. G of z is integral over c to the omega z d mu z, and let's think of it as a transform of, say, a finite measure mu. So can we say tell what are exactly the finite measures for which in this transform g of z is an entire function of finite exponential type?
Of course. This is called Polya's indicator theorem.
Yeah, but then the mu has to live for Polya's indicator theorem. The mu has to live on the real line. The Fourier transform lives on the complex plane, but the function itself lives on the real line, right?
But we have a half space.
Yes.
So if we just end up with thinking of one line, we will not restore a half space. So here's the thing. If you think about functions which are entire, that is analytic in the whole plane, you can always think of its Taylor series, right?
Yes.
And the Taylor series converges everywhere. And sometimes instead of just writing all this Fourier transform, you can just work with series. And the series are more natural to work with because for a Taylor series, let me show here, these are the coefficients. Taylor series has its own coefficients, and you have all these relations. But with functions that are analytic in a half plane, there are no Taylor series.
Okay.
So, I mean, you can take a point, you can think of its expansion around that point, but the range of its convergence will be bounded. So it doesn't take all the points because the range of convergence of any Taylor series is a circle. A circle is not a half plane, no matter how big, small it is. It falls out of half plane. So you never can think of these problems by thinking of sometimes of a Taylor series. So consequently, you can never think of them as type of Pelley-Wiener type of animals who would be restored by a measure that lives on an interval. It has to be a measure that lives on a Messier object. And this was part of my research, trying to understand how messy does the subset of a complex plane have to be, so that if we think of ourselves of measures supporting on that messy set, that must not be as simple as just a subset of real line to restore all functions of, say, exponential growth in a half plane. So this involves some kind of mathematics.
Yeah, that's very interesting. But I want to make a connection with what we already know. Say the Pelley-Wiener theorem for Hardy's half space of functions on the half plane. Of course, these functions on the half plane they are analytic only in the open half plane, the upper half plane, and you interpret them on the real line as in the sense of almost everywhere limit and this
doesn't matter.
So and they do correspond to functions through the Fourier transform. They correspond to functions living on the real line. They correspond to square integrable real valued, well, not necessarily real valued, but
no. Here's the thing. It's a very good point. Here is the thing. Pelley-Wiener theorem, what does it say? If you have a spectrum bounded from -h to h, its Fourier transform is a function analytic, right? Which is some exponential growth and L2 on the real line, right?
Yes.
So I'm saying this again. So you have a spectrum from -h, an L2 function there corresponding to the spectrum. Its Fourier transform is a function that is analytic everywhere of exponential growth. Growth is determined by its h and L2 on the boundary.
Yes, that's the Pelley-Wiener theorem for the so-called finite band function. But there is also a version of Pelley-Wiener theorem just for the Hardy space. It says the Hardy space is the isometric image of, through the Fourier transform, of square integrable functions supported on the real half line. That's it.
Yes.
Right.
Here, when you look at the function g and its boundary values, it doesn't fall in any Hardy space. If it were L2, if it were some kind of growth that you would Hardy space boundary values are L2, right? This is not necessarily L2.
Good.
That's the trick.
Good. That's that I understand. That I understand that you have to go off the real line in order to capture non-Hardy kind of analytic functions.
Yes, exactly. So Pelley-Wiener, every time you could look for Pelley-Wiener, it assumes L2, norm L2, L1, whatever. We have exponential growth.
Right.
That's it. Boundary values of a function of exponential growth have exponential growth. That's it. It's huge.
Yeah. So now the question is this. So you say in order to capture these analytic functions with no whatsoever conditions on any line, I have to take measures which are supported not just on the real line but on the whole plane. All right.
Yes.
Now suppose I take your new transform, which is now working with measures supported everywhere, but I still restrict it to the classical Hardy space. Do I get measures which are supported on the real line, or do I get new things?
No. You get the same. Except, so here's what happens. For Pelley-Wiener theorem, it works as follows. So you have a function which is minus h, right, on an interval. Its Fourier transform is an exponential function of exponential growth that is L2 on the real line. And all this generalization assumes something on the real line. We don't. Now, the thing is, it's an isometry between spaces.
Yes.
So you can determine Fourier transform and back uniquely. Here it is not.
That's what the question was. Thank you.
So you can think, so this is not, so the mu that you can take from the Fourier transform, of course it will work here. But in order to get isometry, you will have to kind of restrict yourself to a specific subset of C of a specific form. Like it has like two axes and then joining them, you know, there are some pictures. So the isometry thing doesn't work as nicely. So I guess the reason, one of the reasons that in every type of Pelley-Wiener theorem, they assume L2 or L2 with a measure is that they were a priori thinking about some kind of isometry between spaces.
Right.
Here, I threw it out, that condition from at first. I don't need any isometry. I want something. And this is why something could work out, not necessarily in isometry. So there are different mu's that would correspond to the same function g. You'd have to restrict them. There are ways of doing that restrictions, but there's no way of doing that restriction on just one single line, because it will end up having all these L2 type or L2 weighted type conditions on the boundary.
Right. So suppose that I abandon the line. I am ready to accept anything larger than the line. But is there kind of an optimal, larger than line, but still optimal universal set which would still give me some kind of bijectivity? One for all in a sense.
Yes, there is, but it's not. There's no notion of optimal there. Will sound strange, I will explain. So think of the following. You know, for analytic function, if you integral over one curve and integrate it over a different curve with the same start and end points, you get the same integral, right?
Right.
So if you integrate this not over the whole space, but over one curve and over a different curve with the same endpoints, you will get the same functions g.
Right.
So if you want to integrate over some kind of curves, whatever curve I tell you, you would change it somewhere and you will get the same set of functions.
Okay. So
there
is no uniqueness.
There's no uniqueness, but you can cook up a curve that would do it. The curve is like it goes from plus infinity to somewhere that turns and goes back. May I, here, imagine here, you have like who and who, two kind of lines going to infinity. Here, and then they're joining each other somehow, doesn't matter. That's a type of thing that would give you uniqueness and isomorphism of spaces or something like that. But it will be like not a line, but a line is like a curve going from minus infinity to somewhere and then to plus infinity, like all the way directly, right? What if you change your mind and crook it halfway? Woohoo.
Okay.
So you think it's something simple, like a line goes minus infinity and then plus infinity, right? And a crooked line goes minus infinity and then it stops, thinks a little bit, and then it goes here.
I'm perfectly fine with that. But if I take that curve, it's not a line.
It's enough to restore everything on the half plane.
So your theory, whatever the results you have obtained, you can do it instead of integrating on the full complex plane. You can integrate just on that fine-cooked curve.
Yes, and these things is called, may I say, it has a physical interpretation.
Okay.
This is called a sweeping theorem. You know, when you sweep the floor with a brush and sweep it, and where does all the dirt end up?
Under the carpet, of course.
At the boundary, right? You sweep the room, and then you think the room is clear, but it's all of the boundary. So this is a type of this is theory of sweeping, saying that a measure acting as on exponentials or on something as a functional is equivalent to the same measure acting on the boundary of the set. So if you look at measures at functionals in a complex plane, it is enough to look at them on some kind of curve. So you sweep that measure out of, so imagine instead of you have a room, it's enough to sweep, it is always possible to sweep the measure to the boundary of the room to the end when it gets this dirty. Why is it enough? So let me explain you. Think of analytic functions. Do you prefer harmonic functions instead?
It's more or less the same.
It has physical meaning, right?
Yeah. Everything we say in mathematics, they have some physical meaning one day or another.
Well, let's say harmonic functions as an effort to go to physics. So if you have a harmonic function in a disk, just a harmonic function on a disk, that is good on the boundary.
Not necessarily, right?
You assume it's good on the boundary. On a disk and on the boundary, it's good one. You want H1, let it be H1. You want be analytic, it doesn't matter. Just on a disk, right? Now, any function which is analytic on a disk or harmonic may be restored by its boundary values. Do you agree? Because this is called Poisson integration or whatever.
Right.
So if you know a function on this boundary, you know it inside too.
Right.
Agree, right?
Right.
So generally speaking, this doesn't hold. Like if you have some general function which is not necessarily harmonic, just knowing it on the boundary isn't enough to know it inside. But if you have a function which is harmonic, knowing it on the boundary is enough. This is called, I don't know, boundary value problems or whatever, right?
Yeah, right.
Now think of a functional that acts on harmonic functions. So associates a number to any harmonic function. It is a functional. So you take a function on disk and associate to it on a number. But this functional on disk may be restored by its values on the boundary. So this functional will be somehow determined uniquely just by looking at the value of function on the boundary. So every functional acting on a space of analytic functions is actually a certain functional acting on the boundary of that space of analytic functions.
Right.
So
makes sense.
if mu as a functional acts on something like a huge part of the complex plane, and it's a functional because you see I wrote integrals, so it's a functional on exponents, it is enough to look at it as a functional on the boundary, and the boundary of a domain in complex plane will be your curve.
Right. That
of
makes
course, in real life,
sense. Yeah.
Yeah, in real life, it gets more complicated if the boundary is not bounded on its own and so on. But you see, functionals are only enough to discuss on the boundary for any PDE which has some kind of initial data programs. So in here, μ's is only enough to consider on the boundary. There's non-trivial theorems on these sweeping techniques on what I said making mathematically sound, but the principle is the same. Functional is enough to consider on the boundary only.
So basically, if you see the measure as an analytical functional, then it is equivalent to another such measure which is supported on the boundary. Yeah.
Yes. I'll give you one example. So think of functions which are analytic in the disk. Just functions analytic. So you know about this dual space. So what is the dual space of these guys?
Analytic functional, obviously.
Yes, so how do you describe these analytic functionals?
There is the standard definition, the dual in terms of the topology of...
I understand. But is there a nice description of them? Like if you know L2 is dual is L2, if you know L1 is dual is L infinity.
Well,
so,
yeah, that's I'm not aware of any such beautiful description of those. You just know that they have to be continuous with respect to this compact convergence topology of the analytic functions.
Yes,
that's it.
And what's the dual?
I don't know. I'm not aware.
Here's the thing. So if you think functions which are analytic in a disk, just analytic, you know, if you think of analytic and somehow bounded, Hardy space, HP, Bergman space, whatever, there's some dual.
Yeah.
If it's just analytic, I'll tell you what the dual is. If it's just analytic, the dual is analytic functions on the complement, which act on these original functions by integration over the ring. So you only need to, as this functional, to act on this original analytic function as a disk. You only need to know the values of this analytic function in closer to the boundary of the disk. It's enough.
Is there a name for that fact?
Yes, Grothendieck theorem.
Grothendieck theorem.
Yes. So you see, it is only enough to know the functions on the verge to describe their dual in a sane way. I mean, this is something that if I say, sounds pretty normal for a physics point of view, but it requests some kind of explanation mathematically.
Sure. So one thing that this brought memories of, you surely know this series of papers by Armen from 1950s, 60s, who was basically in using pretty standard Fourier harmonic analysis techniques to describe the Fourier images of analytical functionals. So this is exactly one way of going beyond the standard Pellegrino theorem. So he says, he asks the question, what is the Fourier image of an analytical function, no conditions at all, say? And the result is exactly certain analytical functionals on the Fourier side.
Yes, for these functions in a disk or in a bounded place, you end up with these Grothendieck theorems. For things which are on unbounded places, you end up with something that I'm describing you with all this sweeping technique. So this is somehow quite known for something that if the half plane were bounded, but quite kind of tricky for things when they become unbounded. See, when you become unbounded, the domain is unbounded. The function could grow really fast, absurdly fast. And to hope for this type of integral representation is hopeless. So what I wrote, I mean, if this was like a sum of delta functions, you would end up with exponentials. So I'm only describing functions of exponential growth. But the thing is, for this Carlson theorem, if the function is much crazier than z, if it grows much faster than z, then this is automatic. So for me, it is only enough to talk of functions of exponential growth to have their kind of interpretation and go on. But of course, as functions of non-exponential growth, any kind of functions, there are also things that could be done for them. The problem is to find normal problems when it will be needed rather than artificially proving theorems. So if you can come up with something from physics,
well, I can definitely produce you a couple such
yes,
situations.
Who grow much faster than exponential functions. So like e to the e to the e to the z. When they're like, when you need to work with them.
Yeah, I guess the way I say it right now is, so what you are discussing might be to some extent an elaboration of Ehrenpreis's results, which are, I mean, these kind of things where you take Fourier transform of really weird functions, weird in terms of their behavior at infinity. Not very many mathematicians are interested in that. So this only those who have had an occasion to go into that know of this work. But so I guess there might be some way to see what you are describing as an elaboration, as a development on what Ehrenpreis was describing in very abstract terms. Now you have a little bit, I guess, more explicit ways of dealing with this object's analytical function.
Yes, so the thing is, what they do and what these Japanese mathematicians were doing were trying to think of dual right away and trying to think of duals of the spaces. And what they were trying to do is looking for isomorphic representations of duals of those spaces. They have Fourier transforms, they have Laplace transforms, they have all these animals. One place that they lacked was kind of simple things like boundary values of analytic functions and so on, understanding them. So, and another that was kind of pulling them down was trying to have this isometry between Fourier representation and the original spaces. If you kind of drop that all, you end up with something as vivid and as this, rather than this abstract theory. Like, as you said, if you think of functions analytic in a disk, its dual is described in terms of kind of, it's a space, it has like it is not a norm space, right? It has this local uniform convergence, I don't know, topological vector spaces. So let's deal with their dual and let's talk about it. But there's a specific kind of tracking down of that, of Grothendieck result that clearly describes the space. So I would have many results of type that if you have functions of some growth, let's talk about the dual algebra of homomorphism and all the arrows and so on. But if you say, okay, at the end of the day, let's track it down and let's have an expression of them exactly in terms of measures, rather than just abstract, I don't know, homeomorphism of abstract spaces, right? So it turns out you end up with something like that. So this is in between the abstract thing on one hand side and this always assuming L2 or L2 weighted on the boundary on the other hand side. And it somehow hits the sweet spot of getting to Carlson's theorem and all the animals.
Right. That's very interesting. Thank you. But I don't want to spend all the time asking questions alone. So maybe the audience is now warmed up and we have more questions for the speaker, please.
I have an incredibly stupid question from slide 4. So you have this transition from one Dirac measure to another one. And could you maybe in a couple of words describe what this transformation like is?
Oh, yes, of course. Imagine the imaginary axis as an infinite rod like that. Like it's I don't know. Could you start video? Could you see me? Oh, let me.
Yes.
Like a rod, an infinite rod, like that.
Right.
And you take this rod, like or lace maybe, right?
Mm-hmm.
And loop it over a disk.
Okay.
Imagine the point 0 is the center. It starts at the 0 as the disk, and then the rod, as it goes up from 0 all the way to I pi, from 0 to I pi, length pi, if you loop it over, it gets to -1, right?
Yes.
And if you take the point -I pi, the distance from 0 is exactly pi, but it goes -I pi, right? If you loop it over, it gets exactly back to -1 again, right?
Right.
So they, if you do that looping, they kind of cancel each other.
Aha, I see. Okay.
Here's from line 4 to line 5. So e to something is, when you think of imaginary axis, is looping it over. So the condition is that whatever coefficients you have, and you think Dirac at these points of rod, you want to loop it over, and as a result, you want this resulting measure to be 0. So if you have I pi, I 3 pi, I whatever pi, not necessarily integers, and you have some values there, the condition for this function to be 0 is that if you loop it, they become 0. So ck must be cancelled out with ck to plus pi on the next kind of, or ck plus 4 pi. So it's not necessarily that all the coefficients need to be 0 for this thing to be 0 at natural numbers, but it is necessary that if you loop it, they cancel each other. So some C1 might be canceled by another CK, which came up from 10 loops after that. And this is a geometric interpretation of the function e to the z. If you think of the function e to the z, like e to the x on the real line, it's like growing like that. E to the z on the imaginary axis is, of course, the sine type of thing. So it's periodic. So you have to kind of, if you go e to something, you have to kind of hit periods and come back to be 0. Again, there is no explanation that I give why this condition relates to this condition. I don't give an explanation on this slide. I just kind of wave my hands around with this looping and give an illustration of this fact, not an explanation. An explanation would be the following. This e to the z transfers half plane to a disk. And this nu becomes the boundary values of this function. And this gn become the Taylor coefficients with negative indices of that function. So gn being 0 somehow will correspond to this function being in some kind of Hardy space. And this being identically 0 will correspond to the boundary values being 0. So in this way of function e to the z that physically looks like looping takes problems from a half space, backs into them into a disk, because you see looping is on the disk, right? Turning axis on a disk, other axis will turn into smaller circumferences inside the disk, and also half space in this way will turn into a single disk. And for a disk, you have a theorem. And the theorem is rather neat. You see, you can only allow f to vanish on a subset of measure 0. You cannot miss a single interval. as a consequence. And here it says, well, after looping, you have to have all the minus pi I interval. And this says, can't even miss something. This says, you know, these 2 points, minus pi I. Here, I don't know, something. And here, everything, so all the frequencies must be there, all the frequencies, to kind of mimic a situation where Gn equals 0 on natural numbers, but is not identically 0. So situation when Gn equals 0 on natural numbers, but is not identically 0, if you look at its spectral picture, it's rather messy. There's a lot of things going out. So if it's very simple, like if its spectral picture is all the spectrum from 0 to, I don't know, 1/10, definitely it cannot be 0 on natural numbers only. It will just be 0 everywhere. So there's some kind of messy cancellation going out, due to which you can become not identically 0, but 0 on natural numbers. And this thing makes this theorem only on measure 0 much neater than Carlson's boundary uniqueness theorem. So in terms of this Shannon-Nyquist theorem, what it tells is that if you have it 0 on natural numbers, you know, Shannon-Nyquist says you have to have and non-zero naturally, right? So 0 natural numbers, but not identically 0. Shannon-Nyquist says you have to have a really huge bump. Because if you don't have really huge bump, if you wave smoothly, being 0 on zeros on natural numbers is enough to claim it's 0 everywhere, because it's 0 here, 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 and smoothly change, so it's 0 everywhere. But what I add to it is that if it's 0 here, here, if you allow bump, right? Then in order to keep 0 it everywhere, there should be some kind of horrible mess of bumps that should cancel each other in some strange way to allow that function to happen. So Shannon-Nyquist says it's identically 0 if you don't allow huge frequencies. I say if you allow huge frequencies, then it should be identically 0 only if these huge frequencies cancel each other somehow, something that Shannon-Nyquist doesn't tell at all. So this is in addition to Shannon-Nyquist I'm saying, because Shannon-Nyquist doesn't say anything about huge frequencies. Once the step falls out of it, Shannon-Nyquist says, well, I cannot restore it. And I say, well, you cannot restore it, but the reason you cannot restore it is the functions that you cannot restore is not just functions that have one simple bump. It's just whole messy things.
Interesting. Really very, very interesting. Thanks for the explanation and for introducing us today to all these fascinating topics. I mean, I really had no idea about anything, and now I learned a lot. Thanks.
So thanks. Any further questions, please, for the speaker? So if we have no further questions for the speaker, then I suggest that we conclude the formal part of the seminar. Thanks to everyone. So I stop recording.